Faraday's law says that the changing magnetic flux induces a current in the conducting loop, but charges only move if there's an electric field. So this must mean that the changing flux induces an electric field. And that's what's sort of illustrated in these two little pictures. We get a current. So there must be, in a region of increasing B field, we get a current looks like this, which means there must be an electric field pointing along the direction to keep the current flowing. But the conducting loop is unnecessary. The electric field must be there by dint of the changing magnetic flux. Right? Notice that it's different from the kinds of field we talked about before. It doesn't start or end on any kind of charges. It just is. Actually, this is a little surprising because it looks kind of like a magnetic field, which also doesn't start or end on any kind of fixed charge. Right? But we end up saying that we get this kind of circulating electric field that would stuck together would look like that. Notice around that any closed loop, the work done by this electric field is non-zero, right? We're talking about currents. We move current around that loop. We would get E dot ds along that whole loop would never reverse direction, and so we would never get negative. We'd only get contributions, so we would have some non-zero work. So this electric field produces forces that are non-conservative. We need to be really careful when we start talking about is electricity conservative or not. In static cases, electricity is conservative, but with changing magnetic fields, it is no longer a conservative force. That means we can't define a potential energy for it either. However, we can connect it to the EMF that it produces. That is, the EMF is the work around a closed loop over a charge, and the work around the closed loop is QE dot ds. The charges, of course, cancel out, and we get that the EMF is just E dot ds. That means that the rate of change of magnetic flux is minus the integral around a closed loop of E dot ds. The negative sign is to respect Lenz's law. Right? That's notice before we kept doing things in terms of absolute values to avoid having to worry about this, but now we're going to say quantitatively that the change in the flux has that minus sign, and that guarantees that the induced field will be to reduce the flux. If we increase the current through this solenoid, that induces an electric field that circulates around the magnetic field lines. There's sort of a cute thing going on here where the field of the magnetic field, of course, is like this, and the electric fields now circulate around, wrap them around essentially. And if we're looking into the solenoid from the top, we'd have that the electric field is circulating like this, and of course the B field would be coming out. You might wonder, is there anything deep about this? But actually there's something tremendously deep, because this is now connected electric fields directly to magnetic fields, although it's only through their changes. This is eventually going to lead us to Maxwell's equations, which are the fundament of classical electromagnetic theory and sort of the model for almost all modern theories. We'll see that changing magnetic fields will produce an electric field, and changing electric fields will produce, as we know, magnetic fields. So therefore, these two will feed off each other and reinforce each other, and that will be a big deal when we get to Maxwell's equations in a little bit.